test is Wednesday. So we did 1 and 4? No. 2 and 3, of course. Yeah, 50, 50, chance I picked the wrong ones, right? Okay, so check your answers and see if you have any questions. You're just finding where the x is, taking out the value of y, and then in this case you're just adding them together. I just left it as a point. You didn't, your directions didn't say graph the results, did it? No. So you didn't have to worry about graphing the results. Just look at the y values then. Just find me the y's. I probably didn't copy that part out of the book. Again, find your x. The value of your function is your y value. Plug them in. And you didn't have to give the points if you didn't. Good with this?
Yes.
Okay. Okay, what was the next one? 5? Okay, so 5 you had to do all the functions. Add, subtract, multiply, divide. First off, were there any domain restrictions in your original functions? No? What are these guys when we graph them? Lines. So they're continuous, they're all real numbers, no domain restrictions. You're just adding your functions together, combining like terms. Make sure you combine your like terms. Don't leave it like this. When you subtract, watch that minus sign. You're subtracting the entire thing, not just the first term. So negate each piece. Combine your like terms. Multiply, distribute it out. And when you divide, you can leave it like this. You don't have to rationalize anything. But you do need to give me a domain restriction. Find it now? Okay. You have to give me a domain restriction. Take out the one that's going to make the denominator a 0. All you have to do is just put the domain right next to it. Because when we divide, we can't have a 0 in the denominator. Pretty easy, makes sense? Did I give you 6? No. Because it's basically the same thing. This one had no domain restrictions. This one did when it did a divide. 7? Okay. I gave you all of these. They were quick. You could make the equation first if you wanted to, and then plug in the 3, or you can just plug the 3 into F, plug the 3 into G, and add them together, whichever way you prefer. Since you're only doing this once, I would just plug the number in, add them together. The divide, since they're numbers, you have no problems with the domains. And always reduce your fractions to lowest terms. Always simplify your radicals. Always combine your like terms. That's like an unwritten statement in precalc. Good with these? Okay. Did I give you 11? 11 and 12? Okay. So in 11 and 12, you had to do f of g and g of f, and then you had to tell me if they were the same graph, if they were equal to each other. And they're not in that case, and in this case, they are. Now, on Thursday, we're going to see when they're both equal to x, they're equal to the same value. These are inverses of each other. I don't know if you remember that from Algebra 2. When you plug one into the other, and they both come out to be x, those are true inverses. That means their inverse is also a function. It means their original was a one-to-one. Good. And I give you these guys, right? I did, yes, because these had values and these had which ones you had your compositions. So the compositions work a little bit differently again than your functions. Again, I would plug in the 3, and you have to with the graph. And then this one goes into the G, start at the right, go to the left, start at the right, go to the left. And you can see here that these are not the same. questions at all?
Can you go back to the
Sure. This one? Mm-hmm. To be a true inverse, you have to be able to do f of g of x and g of f of x, and they both have to come out equal to x. These make us inverses of each other. But all you had to do was tell me that they were both equal.
number 11, you only like the domain for
For this one, this was the only one that had a domain restriction.
Oh.
So that's going to be for the whole thing. Because you're going to use both functions. So your domain for that whole thing, this one had no domain restrictions. This x is not in the denominator. It's technically in the numerator. Okay, let's pull this together. This is a good exercise for compositions and for domains. So everybody okay with this up here? An easy way to do this is box in your area. Box this in. Now, this is your x-axis from here to here. So your x-axis going from -4 to +4. This -4 is open, so that's a soft bracket. This +4 is closed, that's a hard bracket. Your range went from -5, just use your y-axis, from -5 to +4. Your -5, since it bounces off that point, that's a closed point. Your +4, both of those points are open. Box them in. Is this a function?
Yes.
Yes, it passes a vertical line test. One's open, one's closed. This is like a piecewise. Kind of like a piecewise. Where I say domain from here to here, domain from here to here, and we give you the domain. Stop me if you have any questions. Again, box this in. Come across, come down, and come down here. So your x is going from -5 to +5, and your y is going from -5 to +5. In your x value, that -5 is closed. That gets a hard bracket. In your x, that 5 is open, soft bracket. And both -5 and +5 in your y are open. So that's a soft bracket. Is this a function? Yeah. It passes the vertical line test. One's open, one's closed. You had to subtract these. Were there any domain restrictions at all in a parabola and a line? No. Think of what the function gives you. There's a parabola and a line. Right away that tells you no domain restriction. So be careful of your subtract. When you're subtracting the g, make sure that's in parentheses and you distribute your -1. You don't have to factor, you can just leave it like that. We gather all like terms. That's actually standard form, x squared, x1, x0. I mean, most of these things like that. When you can factor and reduce, then do it. This guy, you had to divide. Originally, there were no domain restrictions. Originally. This was a parabola, this was a line. When we divided, this one you could simplify, because this one is your perfect square factors. Now we can take out a common factor and be left with this. However, this guy gave us a little bit of problem. This cannot have a 0. At any step of the way, it cannot have a domain restriction. So you got to take out the 4 out of your domain.
Like, even though it's simplified, it
Mhm.
doesn't have any.
Mhm. Yeah, because technically when we plug it in, we would plug it into this one, right? When we graph, if you graph this versus this, are they the same thing? No. So it's this, although we simplified it. Yes.
So if the original equations that we were given had a domain restriction, we keep that one correct?
Yes. And the only time you would have to revisit it is with a divide. Because sometimes in a domain restriction, okay, so say this was 1 over x squared, just for instance. So you couldn't use a 0. When you divide it, it might give you a further one. It might also say, okay, now you also can't use something else. Well, then that will be your final one. You take what you had and then you just modify it. The only one that does that is the divide, because it's giving you a denominator. Okay? But this one had no restrictions to begin with. Okay, again, this has a parabola and a line. There's no restrictions. This is a multiply. I don't know, did that look like a multiply? You took it as a multiply? Okay. So you're going to multiply both of these binomials. Make sure you distribute them and just collect your like terms. Leave them in descending order. Six, again, was a parabola and a line. You're just adding them. No domain restrictions.
You don't put them in binomials?
No, you can leave it like that. You don't have to factor. Only factor when you can reduce, and only factor it if you can reduce. You know, like if I had x plus 4 underneath in the denominator and I couldn't reduce it, don't factor it. Plus that one, you would have to factor out a negative one besides. I wouldn't even, just leave it. What we consider the proper way to do it is we standard form. X squared, x1, x0, go from highest exponent to lowest exponent. Keep your variables in alphabetical order. Here we have a little domain restriction to start with. We have a domain restriction because your denominator cannot be 0. So this is your domain right now. This is our domain for whatever follows. And then we might have to revisit it. So when we get to here, and you're plugging G into F, and you get this, we still have this domain, but we have no additional restrictions. No additional because there's nothing I can put into this X that's going to give me a 0 down here. But we still have the original domain restriction. If at any point in time you do something different, you have to check your domain. Questions? Okay. This is a good exercise on domains. I think these are the rest. This one has a domain restriction. When we put function f into g, we also still get an x in the denominator, and the only thing that still affects that is a 0. So there's no additional domain restriction. And we still have this domain. You just write it once, and that's it. Now this next one, remember, is a quadratic inequality. Watch underneath this radical. This is, when you set this greater than or equal to 0, be careful because this is a quadratic inequality. So let me pull this one up. You set it greater than or equal to 0, you find your critical values, but remember you have to test. You have to test all 3 sections. Whether you put this in your calculator, x squared minus 49, or you say, it's a parabola that opens up, I can tell my y's are positive here, my y's are positive here, my y's are negative here. I want the positives. I want the greater than or equal to 0. And I can use 0 because there's no denominator. So there's my domain for this one. This one has no domain restriction. So this is going to be my domain for everything. At this point over here, do we have an additional domain? We're still here, and we're good. We're still at the plus or minus. It's right back to where you were. Yeah, a squared and a 2, any of the evens will have the same greater than or equal to 0. Then we stay in the real numbers unless we're specifically doing complex numbers. Yes, Amanda. This one puts you into your imaginary numbers, so we just get rid of it. This one. And then we had a radical in here, so we have to look where your radicals are. Your radicals came in here, so we didn't have to worry about those. We still stayed with our original one.
If we stayed in the original one, why do we put additional ones?
So what happened here is, we can't use this one. That puts us into imaginary. We get this one plus or minus radical 7. Here's your number line. Here's what you have so far. Right? This is from this. Agree? Now where's your radical 7 fall? In here? In here. Technically this would say, goes here to here. But this is where we are right now. So if we took this piece here, it would never work for the original one. So we get rid of these. We still keep the original one. Remember, you're going to do where they overlap, right? And where are they going to overlap? Right back to where we were. Okay? One step at a time. And the imaginaries, don't worry about those. Okay, so you have a review to do.